What I'd like to do is establish the determinant as something that calculates area in a 2 by 2 case or volume in the 3 by 3 case. So what I have here is I've got two vectors. Let's say this first vector is the vector AB. So that's A and this is B, and then the second vector here is CD. Okay. And what I want to do is I want to determine the area of the parallelogram determined by those two vectors. Okay, so there's my parallelogram, and I want to find the area. And the way I'm going to do this is I'm going to chop it up into some pieces. I'm actually going to draw a rectangle here with side length A going this way and side length D. So it's A wide and D tall, that rectangle. And then I notice that this corner right here, I'm going to connect that to the corner of the parallelogram. And then what I'm going to do is I'm going to take these pieces that are outside of my big rectangle here. So I've got this rectangle. Notice the area of that rectangle is A times D. So I'm going to take this piece here, and because this is parallel to that, and this vertical side is parallel to this, I know that this piece will fit right in there, and that this edge here will be right over here, parallel. Let's see, it goes down 3 over 2, so it's going to come right to there. Right? So this and this will be parallel. So I'm taking. Let's see if I can do this. I got this area right here being translated over to this area over there. Okay? And likewise, I want to do the same thing with this triangle and slide it down there. So I've got this thing here parallel to this. Okay? And let's see, let's give a little bit of color to this. So let's make this a little darker green here. So this bit is being translated down there, and again I know that it fits right in because I know that this side of the parallelogram is parallel to this side, and that this horizontal is parallel to that horizontal. I also know that the length of this side is the same as the length of that side, so it fits right down in there. And so what I see is I see that the area of the parallelogram is the same as the area inside of this rectangle minus these two little triangles. Right? So let's see if we can write this down. Whoops. Why did I just go backwards on that? There we go. That's what I want. So I have the area of the parallelogram equals A times D, because that's the area of the big rectangle, minus this piece and that piece. Right? Well, how big are each of those pieces? Well, I noticed that the height of this one right here is the same as the height, it's B, right? I also notice that the width of this one right here is C. And what I want to claim is that they're both the same. And actually I see that they're both the same because of one of them is right here and the other one, this one, is right there. So that this width here is the same as that. That's the distance that you move over here. Well, that was the C from this one. Likewise, the vertical piece here is the same vertical piece there. That's B. And so the total of those two triangles is B times C, which is the determinant of A, B, C, D. So you got one vector, you got the other vector, you make a matrix out of them, and you've got the area of that parallelogram. Now, there's a little bit of hand waving that I've done here. Actually, probably a fair amount, but it's not really the area, it's the signed area, because I don't I mean, in this problem, I made it so that A was bigger than C and that D was bigger than B, and maybe it's the other way around, and what we're getting is a negative thing here, but plus or minus, if you take the absolute value of this, you've got the area of that parallelogram. Okay. Likewise, in a 3 by 3 case, when we look at vectors in 3D, you've got, either in a linear class or a Calc 3 class, you learn things like the length of the cross product of two vectors is the length of one times the length of the other times the sine of the angle in between them, right? Which is the area of the parallelogram. If this is U and this is V, then the parallelogram has area base times height. Well, the height is that hypotenuse times the sine of that angle. Well, that's exactly what this is. So this is area of the parallelogram. Then we look at the notion of the triple product, where you have something like U dotted with V crossed with W, right? Where, I mean, you calculate V crossed with W using a determinant. You say I, J, K, V1, V2, V3, W1, W2, W3, right? That's the way that's calculated. And with the dot product with U1, U2, U3, I mean, the dot product is calculated as the first component here times the first component there. Well, the first component here, these are all vectors, is, actually that should be an I times this little subdeterminant. So that's the same thing as putting a U1 right there, and then you're going to multiply that by this little subdeterminant, V2, V3, W2, W3. Likewise, the second thing in this dot product is U2 times the second component over here. Well, the second component over here is negative J times the subdeterminant with those two. Cover this up, cover that up, that thing, right? And, well, that would be equivalent to saying, well, just stick the U2 right in there and take the V1 and the W1, and then, so you've got this times this subdeterminant, you've got that times this subdeterminant with a minus sign, and then you've got U3 times the third component of this, but the third component of this is gotten because of the K right here, so it's just this subdeterminant. So I might as well just put the U3 right here. And so this calculation of the triple product is the same as this 3 by 3 determinant. The triple product is a dot product, so this is equal to the length of U times the length of V crossed with W times the cosine of the angle in between these two vectors, right? And so the thing is, if you've got U, V, and W, so V and W make a parallelogram down here. The length of this cross product is the area of that parallelogram. The actual cross product itself is perpendicular to both of those. So when I look at the angle between U and the cross product, that's this angle right here. That's the theta that I have drawn right there. And so then the length of the cross product, well, let's put it this way. This length of U times the cosine of the angle, the length of U times the cosine of the angle is actually this length right here. It's the distance from here to there. And so if I have the area of this base, which is this, times this height, it is exactly the area of the parallelepiped determined by those three vectors. Right? So this is equal to the volume of the parallelepiped. And I don't know how many parallelepipeds you've ever drawn in your life, but I've drawn a few of them. Anyway, they look like, you know, kind of squashed cubes. So the 2x2 determinant is calculating area in the plane. The 3x3 determinant is calculating volume in space. And we're going to use this in our change of variables stuff.